Good evening, May 21st, 2023. I've been reading about the differential or the integral equations and otherwise f of x, y, y prime or f x, y, p, where p is dy dx. And there's been some considerations about, exploring the idea was that there was the hyperbola, it's a reciprocal function, 1 over x. This is a hyperbola that's the inverse of x equals 1 over y equals 1 over x. The variables are replaceable to each other because they're symmetric about fx equals y. This identity dimension. And then this is the second idea. And then how that arrives is it gets into what are called singular solutions to the differential equations. So I'd rather somebody had kind of explained this to me before. They drew an analogy and a metaphor between division by 0 and something that's not defined, or what becomes an indeterminate form when it's 0 over 0 or infinity over infinity. That these singular solutions are in a sense indeterminate forms, but they do have solutions in various cases about that indeterminate forms have various conditions that make it so that they're not indeterminate anymore. They have real analytical character. And so they're not so much voids as spaces to be filled, that this tenuous connections within them can exist about the tendencies and the tenuosity and the tenaciousness, as it were, of the ability of the systems to paste over them or paper over them to make it so that they have solutions as about them. And then there's, for this identity dimension, that in this differential analysis, and in particular as I've been reading it from kind of the old school way. And so the old school way means, at the fin de siecle, which is the year 1900, say, because the year 2000 is not called fin de siecle, but the year 1900 is, because basically it's when the world changed from French to English or something like that. But then in the year 2000, nothing like that happened. And so we just call that year 2000 or Y2K. But the fin de siecle in differential analysis was very much as about the plane curves and the in their integral equations, and then methods of finding solutions of same. And these are largely algebraic, and that they also have some various notions that are kind of like about linearizations and stuff, but mostly not. It's pretty much absent these submersions or linearizations, or the submersions and immersions of the differential geometries, numerical methods, initial segments, terms, or whatever, kind of like the approach to this differential geometry book. And this then for what is the modern curriculum today in differential equations and the partial differential equations, the means of linear analysis, and basically getting up to Sturm-Liouville, or then getting to apply methods of transformation after that. But a lot of things that go on in the exact and the solutions of various forms of mostly linear ODEs, and then about the partial, usually in the nonlinear ODEs, where those are found to exist at all. And these kinds of things make it so for that the ideas of this earlier time, which some might have as more or less general, and not as general in the sense of being tractable to methods of numerical methods. But at the same time, they have some things that emit solutions. For example, what result being submersions that have all their character in some finite initial segments, and otherwise these series, and the series analysis, that then when the Fourier analysis comes up as being very central and just general and regular in the milieu of these things, that's possible to consider why variously these what you would call curriculums, the curricula, that it ends up how it so results that the view from the fin de siecle and the differential equations in their solutions, and their integral equations in their solutions as for plane curves, has really a wealth of knowledge. And one thing that's kind of lost without that kind of context is that there are some things that are plain in plane curves, and plain as in obvious, or clear or otherwise easy. In the plane curves, those are the surfaces that are two-dimensional and of the geometrical character of a vector space like R2 that are not so in otherwise the milieu of the coordinate setting and generally this attainment to the complex analysis and the Wronskians and these kinds of things, which again end up being a very sensible, fungible, and tractable milieu, but closed in its way, and that when you have these various subfields that each kind of have this common core of elements, but then each build their derivations out in different directions, that it doesn't become sensible and fungible to mix and match their results together. But it sometimes becomes so that really the most concise derivation is of an agglomeration of these different fields together, and so that's why it needs sort of overall approach. And then the idea of this overall approach is to identify where things like differentiable geometry decided that there's no zero anymore besides no infinity, or plane curves have singular solutions which cannot really be defined in these other ones, or that the PDEs are not like this fuller analysis about the cusps or things to do with the osculating, or otherwise some of these methods, what this envelope brings of methods and solutions, that then it kind of demands then that when differential topology or what brings up things like the pseudo differential, that how it is so it requires more than less this idea of this descriptive differential dynamics to put together all the concepts of the differential in one kind of overall field. Differential dynamics, and dynamics not just in the values and the solutions and the equations and the formulas, but also in the definitions. So that then it becomes possible to consider a way to read any given development in any given setting, to translate its elements to those which describe and define all what's so for that setting, and then have developments among various settings have a translation among them to be able to establish what's so and how it holds in one, and what's the necessary import of one to the other to have well-defined definition, and where they run together and when they run out. That otherwise that there's a proper conscientious approach to rigor and formalism. So that being just kind of the desiderata and requirements of this descriptive differential dynamics, which began as just sort of a survey, what is differential dynamics and how is it descriptive, thus that it has an ontology of terms that makes so that it's fungible after being sensible, and thus that it's tractable altogether, that this is a kind of approach and hope. So, as I was looking into the methods of this singular solutions yesterday, and there's a bunch of papers from like 1897 and 1894 and 1887 and 1903 that by this time there had been accumulated after Cayley and after Salmon's book, or Salmon's book on differential equations, a treatise of sorts, and a collection of all the colloquia and over the day, and the contributions in the series and these kinds of things that went into it about the fin de siecle. This book in the University Mathematical Text, of course, is from about 40 or 50 years after that. And so then, as I'm getting into it, I wonder where it will basically reflect the change of this development into what gets into the differential equations. And I guess it's kind of when it gets into linear equations, these solutions of the linear equations, because you figure that these solutions of the linear equations are going to be pretty much the same ones that they have about e to the x and the differential operators and the ability to place things into the series, and that here, as I'm just kind of scanning forward, then we get into complex analysis and see a differential equation for an electrical circuit, And they introduce another delta, another variable for a differential. It's kind of like an extra scripty D, and I'll have to find out back what that was, vis-a-vis the scripty D or Greek delta for the partial differential, and Latin D for the differential of Leibniz. Variation of parameters. We get into some variational series. So chapter 6 is solution in series. And so by the time that this book is kind of about 2/3 through, or 3/4, then it gets into some of the same solutions and methods that we have with regards to the usual curriculum today. But and which ends up being pretty general, but it's not necessarily something that would be tractable in a time where in pencil and paper they want to get exact solutions particularly, and these kinds of things. But then it does get into this regular singularity, and so with that kind of, with the idea of just kind of skipping around a bit, but then it has with regards to the hypergeometric equation, and that's something that deserves its own sort of analysis. And then on the genre, and Bessel, these special series of integers defining coefficients that via providing tables for their computation or tabulation make for the ability to read off these initial terms. That after the table of the logarithm, for example, that these tables of these other series become really much a kind of a thing. Then that there's the solutions and the examples in the book, briefly, and the index of this book, about that the singular points were defined again early, but then this and later in the book. So we'll look to the singular points at 35 and page 115 where we'll begin. So on page 35 it says, points at which the gradient becomes indeterminate through the simultaneous vanishing of P and Q are said to be singular. So P and Q is that P xy dx plus Q xy dy equals 0. So anything that can be written in terms of P xy dx and Q xy dy equals 0. So anywhere that that's 0 over 0, P over Q, that's singular. Signs the value y prime equals negative P x y naught x naught y naught over Q x naught y naught to the gradient at that point. And this value is determinate with the sole exception of the case P x naught y naught equals 0 and Q x naught y naught equals 0. And then with regards to then it began the description of the linear fractional equation and explaining about how then this a whole x equals y is right in the middle of that of sorts. The singular points are the points of intersection of the curves P x y equals 0 and Q x y equals 0, which are the loci of points at which, so the points that match those, or the point set, so the lines, the loci of points at which the integral curves have tangents parallel to the x-axis and the y-axis respectively. They are thus, in general, isolated points. So reading now into this a little bit more, changing my voice a little bit, then further in chapter 53, in page 115, or 80 pages later, regular singularity. When we consider an equation of the form pxy double prime plus qxy prime plus rxy equals 0, so that our functions in x, in terms of y's second derivative and first derivative and y itself, the function equals 0, we see that if x minus a is a factor of the coefficient px but not of both qx and rx, that equation fails to determine a value of y double prime for x equals a, and the procedure of 52 is inapplicable, whereas the procedure of 52 is a Taylor series. Solution is developed as a Taylor series, where x equals a be a value for which p, q, and all derivatives are finite, we shall obtain a solution such that y and y prime have assigned finite values y naught prime when x equals a. And obtaining the corresponding value of the second derivative, y double prime naught equals PA y prime naught plus QA y naught, differentiating obtain y double prime equals px y double prime, or excuse me, y triple prime equals px y double prime plus this quantity p prime x plus qx quantity times y prime plus q prime x of and times y, and as y naught prime, y naught double prime are known, y naught triple prime can be obtained immediately. Continuous process, obtain the values as successive derivatives for x equals a, and thus we have that the coefficients in the Taylor series are as of y equals y naught plus y naught prime x minus a plus y naught prime x minus a squared over 2, bang, plus dot 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 plus y naught to the n, the derivative x minus a quantity to the nth over n factorial, n bang, plus dot dot dot. Borrowing from the language of the theory of functions of a complex variable, a point at x equals a, which the above conditions are satisfied, is said to be an ordinary point. So the ordinary point is where there's not indeterminate factors and they're finite, and then so works out that then those can be all bracketed out and built together and put down. So here, when that's not applicable, we then say that x equals a is a singular point or singularity of the equation. So this is kind of so whenever there's not a second derivative. If x minus a is a factor of the coefficient px, which is on the first or highest order term, y double prime, and this gets into why in the operator theory, the idea of considering the derivative and the antiderivative is reciprocal operations, in that it operates on functions, vis-a-vis that it operates on values. It goes a long way for the algebra of these things for keeping them together. But then there's this question about what it goes into. The form of a solution valid in the neighborhood of a singularity may therefore differ from that of a solution appropriate to an ordinary point. It is important to investigate this difference, which is not merely a matter of theoretical interest, but of practical importance, as the solutions valid in the neighborhood of singular points are, as a general rule, those required in physical applications. We find a clue to a fruitful line of approach in the equation x minus a squared, x minus a quantity squared, y double prime plus b times x minus a quantity times y prime plus c y equals 0, where b and c are constants. So here there's that, it's in the second power of x and of y prime, and then the first, and then the 0th, or cy is just c times x to the 0 and y to the 0th prime. So it's kind of like x, y, and then combining the operation of taking the power of x and the derivative of y at the same time, where b and c are constants. This equation has a solution of the form y equals x minus a to the sigma, so that the singularity of the equation may apply a singularity, for example, a pole or a branch point, in its solution. When pxy double prime plus qxy prime plus rxy equals 0 can be written in the form of the quantity x minus a quantity squared p1x y double prime plus x minus a q1x y prime plus r1x of y equals 0, such that p1a not equal to 0 and p1x q1x r1x are finite in the neighborhood of x equals a. It is thus natural to assume a solution of the form y equals x minus a quantity to the sigma f of x, where f of x is a function which can be developed as a Taylor series in x minus a. So for Taylor series, that's something to study, whereas the two big series are Taylor and Fourier, in a sense. But although any given orthogonal functions can make a series that make for various treatments to approach their coefficients in various settings. And then about power series, and then about the diminishing terms. and these kinds of things. For a couple usual series that are either of powers less than 1 or that are scaled down, for example, by the factorial or a growing term. So series that are scaled down or series that power down. Taylor or Fourier series. Are finite in the neighborhood. Thus, it is natural to assume a solution where fx is a function that can be developed as a Taylor series in x minus a. It will be found on substitution equating to 0, the lowest power of x minus a, that sigma is determined by the indicial equation of the second degree. Sigma times sigma minus 1 of p1a plus sigma of q1a plus r1a equals 0, giving in general 2 distinct values of sigma and leading to 2 distinct solutions. Such a singularity is termed a regular. So then this gets into a refinement of the notion of singularity with regards to the regular singular. And then here, with regards to this first and next order, one of these operations I'm thinking about taking is what about a solution that is, it's kind of like for family functions taking as derivatives. For another family functions, that same operation takes the integral. Like these are functions that basically are kind of reflect the opposite of a differential function, this integral function, that it has the same kind of ordering as in terms of the rank or order of taking the power, but in the products together, then taking one according to this operator calculus is as of the operation of differentiation, and that the other one is like the integral. And now the reason I bring this up is because if you take the integral of 1 over x, it's ln x. And if you take the integral of that, then it's x times the quantity ln x minus 1. And so when I look at the sigma minus 1, and I think about x and ln x, and then that being like the second term, or this, that's like, well, what if this is x? That x squared is kind of built as about this way, in terms of x and a and it's constant, and where x and ln x minus 1 and it being this thing. And that's kind of, the floor of, where it can reach to, kind of in these notions of the hypergeometric functions and minus 2, which is about functions that are differentiable at least twice, and thus we can make any kind of definition with the Laplacian being equal to 0 is called a hypergeometric, or called a harmonic function, that this harmonic kind of function is sort of defined like this. Here, this is kind of like an anti-harmonic function in a sense, but not really, because what it's really about is that there's this operation that's kind of a reverse to differentiation. It's called integration, fine. And then there's this notion, like, well, what about the term that taking the power is the same thing as taking the integral? Oh, who would have invented that? Why would you make those together? Well, here the idea is just like you can end up having an addition formula in powers. It can be a very useful thing. Here the idea is to take this sort of integration formula, or this otherwise under the operator calculus, to make it and live in an algebra where taking these powers or raising it into these ranks makes it so that there's some kind of power formula, power-taking formula, that can work up these integrals. And the reason why I want to make it so like that, because then I figured that there might be a very simple kind of function to do with x ln x p1a, or in terms of sigma and sigma minus 1 p1a, and then sigma q1a, that would be some sort of p1 in q1 and r1 in terms of a, this constant would still be kind of like constant functions, but just these offsets more or less of it, and vis-a-vis x, and then plus r1a equals 0, where sigma is this x minus a anyways. So figuring to build out x minus a to sigma, and get sigma figured out in terms of the parameterization and what it means in terms of these, just as an example, because it's particular, the integral of x to the negative 1, or 1 over x, and the integral of that, and so on up into the integrals of ln x, but pretty much just to get it to where so that there's a way to figure out for f of x equals x, this identity dimension, and then this inverse of the identity dimension, because the idea is to be making this sort of space that will make for an analytical region that will allow some of these kinds of otherwise singular conditions have closed forms. And thus, then the idea is to frame stuff that builds to those as about a thing. So that's kind of the new idea fix, is about the operator calculus and power taking formulas that are like addition formulas that you can figure out how to compute the product of some things by adding up their indices, like taking the product of powers and summing their exponents and thus computing their product. The idea is then for these formulas in the differential equations, where it's in terms of x and y, and it's in terms of powers of x and orders of differentiation in y, for example, to also make it orders of differentiation, in this case anti-differentiation in x, because there are some boxes that will make it so that arbitrarily contrived that is so. There are some conditions that will make it so that under these formulas that kind of thing can live. So these are the kinds of ways to look into means to enable that once it's set up, then whether the problems are anything more than trivial or contrived is something that would remain to be seen. But the idea is to make this up under these formula for making it so that, according to like this kind of indicial equation, which I'll be studying a little bit, to make it so that these matters of form and proportion in the orders and ranks of things, for where they do have addition formula or these power taking formula of these the orders and ranks of the derivative and a derivative, to make them sensible and fungible and tractable in this way, and then to figure out how contrived or not contrived that would be. Now, I said contrived quite a few times, and so the contrivance is basically any kind of fitting the data or fuzzing the data or setting up something that would otherwise be trivial or vacuous, or making an initial condition. Plugging in the values is a contrivance for a solution. To contrive something is just to make it so. Whether it relates to like contrivia or so on, it's kind of like as whether it's not general anymore, or that it makes particular a solution. That's basically what it means. And then what I was reminded was the most contrived number I know about is called Champernowne's number. And in the study of the irrational numbers, there was still a time when it was like, well, can we really prove that these numbers do not have a ratio representing them? We do not have infinitely many computations to trial divide this number by every possible pair of rational numbers to see that it does or does not match. And besides that, there are many series that can add up to them and this and that. And besides that, there are infinite series of rational terms that add up to irrational numbers like Apéry's constant and this and that. So what Champernowne read out is like, well, this number is like this. It's like 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, da 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 da. Which is kind of funny because when you think of the first 9 digits, it's like, well, I see you just place, the nth digit in the nth place, or n minus 1th digit in the nth place. But then when you get out to the 10 digits, then it's 10 or 11, 12. I mean, because I know that decimal isn't even really like necessarily the natural base or radix of numbers. So this is the most contrived number, because basically what he does is he writes out 0.01 to 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, da da da, out to infinity. And so then there's a formula that's rather cumbersome that you can use to determine, is like, well, this will determine the sum of the digits that have been written out so far. And for the next number, this will determine what offset it will be at. And then whether it's got 2 or 3 or 4 digits in decimal, it will just be pasted along. So you can find out what number is at what place in this Champernowne's constant. And that it's irrational. It's an irrational number. And whether or not it's algebraic, it's probably not an algebraic number. No, it's sort of a transcendental number, but it's most contrived. They hear about the least contrived number is 4. Why 4? Well, it's 2 squared, it's 2 plus 2. You might not notice it, but if you have a quadrant, you're dealing with it. Anytime there's a doubling space, there's a doubling space about it. Anytime there's half of things, it was half of 4. You got root 2 and all these kinds of things that are kind of like, what's the power of root 2? Well, it's 2 to the 1/2. And these kinds of things all in terms of 4. Why is 4 the least contrived or most least random number? Well, it's not 0. That's because 0, 1, and infinity are constants, and 2 is just twice 1 already. So those are bounds. So yeah, this is getting into starting to discuss descriptive differential dynamics, which starts first with all regular analysis and in systems of equations and algebra about them that have much more ready means of treating them. You can collect variables and manipulate equations according to the rules of arithmetic and algebra, taking care not to divide by 0. That the differential equations then have, well, what's this function's definition? Well, it's defined in terms of itself as change over time. Why? Well, why time? Well, time is just a particular prototype continuous variable, and we'll use it for everything continuous as a good measure of things. Okay, fine. But then in terms of then these dynamics about it is really why it gets into dynamics. And then, well, is learning differential analysis enough? I mean, what about the rest of mathematics? Well, for analysis, it's enough. There's a whole world of discrete and concrete mathematics where the natural base of numbers is 2 and binary, where here it's a little bit more so in the continuum analysis that the natural base of the logarithm is e, the constant of the natural logarithm. After an APA, or Euler's constant, I guess it's called, for e, but for an APA. That the whole discrete and concrete mathematics, that's about all things to do with sorting, or anything to do with computer algorithms, or anything to do with binary arithmetic or machine integers and the finite and the fixed, and asymptotics of those is a different thing. But as far as the differential goes, then this differential analysis, because it then ends up implementing all of dynamical methods, is the field of analysis this way. And then when you get into stuff like the physics and the total field theory, it's kind of like Einstein says, it's like the physics is a total field theory and it must be defined by a differential by the time. Okay, Einstein, then we need a descriptive differential dynamics if we're going to have a firm grasp on the mathematics of things. And then that is so. And so then with regards to things like probability theory and quantum amplitudes and these things for quantum theory, of course, as well, because that's one of the kind of things is like, well, quantum theory is statistics and field mechanics are differential mechanics, okay? There's as well, the probability is defined by analysis and integrals and this and that. And counting arguments, of course, it's anything that's discrete is a contrivance that can be implemented in the continuous, not necessarily vice versa, but it's kind of so. About the Cantor space of all the sequences of zeros and ones, and square Cantor space, all the sequences of zeros and ones in order. It's a space and square. So here, coming back from the square of the whole xy plane, back down to just our simple first quadrant and x equals y, here's to read off the hypergeometric equation. This is the equation of x times 1 minus x y double prime plus gamma minus alpha plus beta plus 1 times x y prime plus alpha beta y equals 0, in which alpha beta gamma are constants at present unrestricted. On multiplying the equation throughout by x, it will be seen that x equals 0 is a regular singularity. Similarly, the singularity x equals 1 is regular, and there are no other finite singularities. Well, that's interesting, because here, when we're talking about the identity dimension or what, there's various considerations that have gone on to, well, what about when it just kind of flips back and forth between x equals 0 and y equals 0? Those being symmetric about the identity dimension. And so when you have that x equals 0 is regular singularity, we basically doesn't address that y equals 0 if you flip everything in terms of x and y, or have it so that x equals y, that it's symmetric about saying, it'll also be so. Similarly, the singularity x minus 1 is regular, and there are no other finite singularities. Confining our attention to the singularity x equals 0, you assume a series with coefficients in c and the powers in x, non-zero coefficients, c naught, in which the index sigma is, for the moment, regarded as an arbitrary parameter and denoted by phi x sigma. So this is this series. Oh, I see. We assume this series starts with the coefficient, they're non-zero coefficients up to x sigma minus 1. But then afterwards, for x sigma onto dot dot dot, an infinite series of higher order, that this is a series that has 0 coefficients for some sigma many of its initial terms. Then the indexing starts at the first non-zero coefficient and continues. Denoting the left-hand member of the equation by Ly, we find on substituting phi x sigma for y and arranging the terms in ascending powers of x that Ly equals sigma times the quantity sigma minus 1 plus gamma quantity times c naught x to the sigma minus 1. So this is lowering the order of it in a sense. So the hypergeometric brings it down into the order of the thing. Now, the ranges of a series in powers, like a power series is coefficient in each of the powers, each of the positive powers of a number. Now, is there a doubly infinite series that is kind of like a naught x naught plus a1 x to the 1 plus b1 x to the negative 1 that alternates in terms, the plus and minus of the things? Well, yeah, any series that's just coefficients in the positive powers, or where you can resubstitute x with 1 over x and get it in kind of in its negative powers, and then just consider a series with all the alternating terms are just 0. It's like so. But otherwise, it's kind of two series together, one in x and one in 1 over x. And then if you can figure out how that those come together, or that there's solutions that are sums of those, then they can come together. But here, though, and then besides it, for the rising and falling factorial, like the falling factorial is familiar as 10 times 9 times dot dot dot. 10 factorial is 10 times each its lesser numbers. The rising factorial is sort of like, well, 3 times 4 times 5 all up to some higher order power. And then Pockhammer symbol is some kind of name for those, and I forget which one it is. And then there's that the notion of a range of the factorial is very familiar from counting arguments, and so in this hypergeometric it's kind of like the multinomial after the polynomials. That in the polynomials you can compute after Pascal's triangle those numbers, the binomial coefficients. What are for the counting arguments those kind of combinations of things? These are numbers and like Fibonacci's numbers, but here they're just numbers that are usually symmetric in a range of coefficients with a beginning and end that reflect also counting arguments. That this hypergeometric also has a pretty natural geometric interpretation from, besides that later, the first time hypergeometric is introduced is like, welcome to probability 315, and here's the hypergeometric distribution, and here's its gnarly derivation. It's like, well, okay, I didn't quite expect all that. But then when you look at it as just kind of, Pascal's triangle or something like that for the polynomials, it's kind of like, well, when I first learned power series, first I had already been very, very familiar with Pascal's triangle or something like that. So the hypergeometric has a much more natural kind of setting for what it arises from counting arguments and this and that. I'm not quite sure what it is, but here it's something to just leave out then in terms of these usual notions of the ranges of things for products and sums that range over finitely many or infinitely many indices, that these are usual things. Confining our attention to the singularity x equals 0, index sigma, regarded as an arbitrary parameter, phi x sigma, Ly equals sigma times the quantity sigma minus 1 minus gamma plus sigma naught x sigma minus 1, sigma to the x to the sigma minus 1, so one less term, plus the sum of, for r equals 0 to infinity, of sigma plus r plus 1 times the quantity sigma plus r plus gamma times the coefficient of the r plus 1 minus this quantity sigma plus r plus alpha times the quantity sigma plus r plus beta c sub r x to the r plus sigma. So that's kind of interesting because there's some kind of interaction of the terms, the c of the r plus 1 and the c sub r, the coefficient at the rth index and the coefficient r plus 1th index, they're different. So the interaction of the terms is about the difference, and so summing up is summing up these products times their differences. So it's got a kind of addition formula or something like that, just as kind of we've been discussing about in this hypergeometric, that makes it so that this sum of these differences ends up being the same thing as some of these terms by their powers in this things, because after the initial term, then x is not present. Yes, it is, because then the x is sigma plus r term is a later term that's present. So it's kind of a telescoping thing in effect. It's an addition formula kind of pegged to or associated with a higher order term in the thing. Although that's I never really noticed that before, but it's if that's, I haven't seen a derivation here, it's just been presented as a formula. But reading that formula, the notion that it's the sum of the terms of these various differences in these coefficients according to these constants, x to this quantity sigma plus r, that the term only begins with x sigma. So that is the initial segment of the term. So it's not telescoping greater than 0 away, then it's just like offset by r, as r is the index that ranges up to infinity for where those are non-zero. Still, though, it represents this sort of formula that keeps them together. If now, whatever sigma may be, we chose the coefficients, we contrived the coefficients, or find them, that C1, C2, dot, 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 so that sigma plus r plus 1, that quantity, times sigma plus r plus gamma, that quantity, of coefficient r plus 1, equals this quantity sigma plus r plus alpha times this quantity sigma plus r plus beta times the coefficient of r, leaving c sub naught, or the coefficient 0, arbitrary. We find that coefficient 1 equals this numerator sigma plus a quantity times sigma plus b over sigma plus 1 and sigma plus gamma, c naught. And that c2 equals alpha plus a, alpha plus, or alpha, sigma plus alpha plus 1, sigma plus beta plus 1, those terms, over sigma plus 1, sigma plus 2, sigma plus gamma plus 1 times quantity c naught. So then you can find that the ith term, or the rth term, given a formula in terms of the first term, coefficient 0, and so on, as the author writes here. So there's a form of expanding these out because it gives a recurrence relation for the coefficient r plus 1 in terms of coefficient r. And so this defines that taking the nth order of the recurrence relation is just recursing through that in the recurrence relation so many times. And these coefficients are finite provided that neither sigma nor sigma plus gamma minus 1 is a negative integer. So they might be negative, but not a negative integer. So that's kind of remarkable. And it reminds one of like the Riemann's conjecture, or the gamma, the factorial function, interpolated through non-integer values, and that whether or not something like that exists in the negative numbers or not, because it's not defined on various things in terms of the zeta function vis-a-vis the gamma function. Setting such cases aside, we have proved that if phi x sigma equals this series in these terms that's written out this way, this recurrence relation over that, about 1 plus, and then it's related that it's from the 0th term and then an offset plus 1 plus this sum of the power terms in x to the r, and if this series is convergent, then L phi x comma sigma equals sigma times quantity sigma minus 1 plus gamma C naught x to the sigma minus 1. So it's just kind of established that for all this infinite series, you can get back out of it a finite value in a closed form. The question of convergence can be settled one for all by the ratio test for that coefficient r plus 1 over coefficient r goes to 1 as r goes to infinity. And so the series converges. And we can make L phi x comma sigma equals 0 and thus satisfy the equation by taking this contriving that sigma times the quantity sigma minus 1 plus gamma equals 0, solving for that, provided that the stipulation that neither sigma nor sigma plus gamma plus 1 equals a negative integer is not violated. Thus, the roots of the indicial equation are sigma equals 0, provided gamma minus 1 is not a negative integer, and 1 minus gamma, provided 1 minus gamma is not a negative integer. Well, that's kind of interesting. And so that it's not really necessarily clear how to start putting everything in the form of a hypergeometric function and then solving for it in terms of its coefficients and then finding or approaching to these values as they run out and then getting a closed form that basically can compute what was that in terms of any time you need to compute it with new inputs. But it's a thing, if as so. And it gets into like, what are the parameters, alpha, beta, gamma? What do parameters affect the shape and the scale of functions or distributions? Usually when you think of parameters vis-a-vis distributions, is that a given distribution is defined by one of three things. A probability distribution function, which is a continuous function that over the range of the elements has an integral and it equals 1. And then there's a cumulative density function or something like that, which is it's a function that ranges from 0 to 1, and at the bottom of the range is 0, and at the top of the range is 1. And it's strictly monotone increasing. So you have for any given value in the range the probability that it's less than it. And then there's a moment generating function, and that's what I need to refresh my memory about. So for standard probability distributions like so, and then the shape and the scale define that, well, the shape of these functions kind of looks like it has a central tendency, like a mean, or it doesn't, according to the shape parameter. And then the scale parameter is how wide is it, how big is it, whether it's expected values of the sample variance and this kind of stuff. That here, alpha, beta, and gamma end up being these contrived things when you want to write something that's in terms of the hypergeometric function, that this is the equation x times the quantity 1 minus x times y double prime. So it's kind of like when something's, if you think of x only between 0 and 1, when x equals 0.5, then that would be like 0.25. But when x is 0.99 and 1, it'd be more like 0.0, or 0.99 and 0.01, it'd be more like 0.0099. So as it's closer to the middle, it's big, and it's kind of like got a hump in the middle, and as it's closer to the ends, it's small when it's like that on the second power. And so you can see, like, when things, if that's in terms of y double prime, it's kind of like if it's going up a ramp, if it's like going up a ramp and then there's a cliff on either side. And so you got to keep it up in the middle of the ramp, and then it keeps on going, then it may be possible to get up y double prime if you keep accelerating and pushing up the ramp. But then if it falls to either side, then it would, for example, fall off or something like that. Or if it's the opposite of that kind of thing. And then the second term is in x, gamma minus this alpha plus beta plus 1 over x, or alpha plus beta plus 1 times x. I'm not really quite sure how to read the geometric interpretation of those in the thing that was just given, but you might imagine it as in terms of the either side of, the steepness or what, in terms of x, and then going fast enough, you're either more or less likely to stay on the road, minus alpha beta y, which might be then something like how steep it is, as an example of a model to help explain that then you can make a hypergeometric function for this, and provided gamma is we can now make L phi x sigma equals 0. Let's satisfy the equation, and so we can solve in terms of sigma times sigma minus 1 plus gamma equals 0, where sigma was L phi of sigma minus 1 plus gamma is in terms of otherwise all these other parameters. About the L phi of x comma sigma equals sigma minus 1 plus gamma, which is how steep it is. Next, take the alternative index provided gamma is not a positive integer greater than unity. When gamma equals 1, the two particular solutions are identical. We shall assume that gamma is not an integer positive or negative, it is 0, and use the notation of this for the hypergeometric series. F of alpha beta gamma and x equals 1 plus 8 alpha dot beta over the 1 dot gamma times x plus dot alpha plus 1 beta plus 1 over 2 factorial gamma plus 1. And so and plus dot. So alpha plus 2 alpha plus 3 times beta plus 2 beta plus 3 or dot. Writing A and B for C0 and C1 respectively, we may express the general solution of the hypergeometric equation as this thing. The above procedure is known as the method of Frobenius. And so Frobenius, is a guy, it's a school of math, and for him is named like Frobenius norm, or there's some other things about Frobenius that I've forgotten, but he's familiar with some other aspects of this too. So it would be reasonable to consider that studying the hypergeometric would be, it would be possible to study Frobenius and find something else about it. But the hypergeometric is basically very, very general, very general. It's even more general than some of these other systems that make up these linear forms. And I have these parameters because it has more parameters where the parameters basically make, when they have non-trivial contributions each, have that there's more coverage of this kind of thing in terms of that different parameters can make more diverse contrivances. And so more like functions that are with no parameters, like the zero function, like the identity function in a sense. It's got no parameters in a sense, or it's got one, but it's also fixed, compared to a random variable. Well, it formally has none. It's just a random value. But then in the middle are all these functions and formulas that return values, and then in terms of that functions or distributions being parameterized symbolically to make an algebraic function, that a formula can be written briefly, that it has more parameters, makes it more general in some senses, thus less tractable, less fungible, and less sensible. But in some places where it then becomes so, then it's able to collect a lot of different things. The above procedure is known as the method of Frobenius. And then the author writes, it is possible by a modification of the above procedure to obtain the complete solution when gamma has one of the excluded values, but the results are not of any particular interest. The essential feature is that the solution that becomes irrelevant is replaced by one involving logarithmic terms. This point will be illustrated later in the case of the Legendre equation. Well, I guess that's for further reading, because now what I'm taking away from that is these logarithmic terms. All I have in mind of these from mine is that the integral of 1 over x is ln x, and the integral of that is x times ln x minus 1, that quantity. And so I want to figure that in terms of this power-taking formula and this antiderivative operator in the terms of x squared for this, if not for this, so much for this hypergeometric function, about these singular forms that have been addressed here so neatly, and that this regular singularity is as of after the definition and introduction of Taylor series, which is described that a Taylor series is kind of and the Fourier series are complements of a sort. One in powers that are divided, and the other one in powers that are less than one already, so that the terms become small and have a sum in terms of their coefficients, and then in terms of sine and cosine. For power series and these kinds of things and their coefficients, that the Fourier series is in terms of sine and cosine or other orthogonal functions, and as was mentioned, that then for this regular singularity is where the idea is that these applications, the operator calculus, will make, after some contrivances, particular results in the derivatives and antiderivatives of powers, terms of powers, and about this identity dimension, and about those being singular solutions, and about those then staking up what would be indeterminate forms as unitary forms. That these are the kinds of ideas that will might lead to some methods that nobody's discovered yet, or that if they had, they only refer to kind of obliquely, like when he does, it says this point will be illustrated later in the case of the Legendre equation. These are the kinds of things that are possible to consider when one has some extra time, because it's not necessarily likely and usually not contrivable that these would make solutions at all. But where they do, it could be something special. So that will get into the Legendre functions, the Rodriguez formula. Now the Rodriguez formula is very, very famous. It's cool. That's something to be looked at later. Well, all right then. Have a great day. Au revoir.